Okay, then welcome to the first international workshop on virtual fluids. So today there will be 3 theory sessions, and this is the first theory session, in which we talk about the basics of the Lattice-Boltzmann method, in particular the one that we have implemented in the virtual fluids code. So the virtual fluids code is not that kind of a Lattice-Boltzmann solver where we try to implement all the methods that are around in the world. So there are other Lattice-Boltzmann codes that try to accomplish this. So we basically implement what we develop ourselves, and we stick there to the essentials. So we'll talk about the cumulant method, and in particular the superconvergent cumulant method, if I have enough time for this, because this is what is implemented in the virtual fluids Lattice-Boltzmann solver. So I see there are people have different experience with the Lattice-Boltzmann method, and probably even as some of you have experience with the Lattice-Boltzmann method, you may have also used different nomenclature. So I'm going to introduce this in the way we usually see this. So we have the Lattice-Boltzmann equation that we want to solve. And this Lattice-Boltzmann equation we write with an F for the population, which is the probability density of finding a particle in a certain state. And because we have discretized this in 3 dimensions, we write this with 3 indices. So you know from literature originally there were only 1 index used. So in virtual fluids you will find always 3 indices. Yeah. Then now comes a little bit the speciality. These populations are located in space and in time, and our interpretation is actually that they are stored in a staggered fashion. I mean, they are not in memory. The memory is, of course, not staggered, but from the theoretical thinking, from the interpretation, they are stored in a staggered way, which is potentially different from what you mostly read in the book. So the staggered way is like we have a velocity associated with this. So the velocity of this particle that would move in the direction I, j, and k. So this is indicated by the c, I, j, and k, which is a velocity. And in order to make this a space, we have to multiply this with a time step, and we divide this by 2. So this is what we mean by staggered. So it is halfway in between crit nodes, and also it is halfway in between time steps. So it's t plus delta t half. This minus, so this is what we call a pre-collision state. So this is the state of the population before they undergo collision. Yeah? And on the other side we have, or on the same side, because we put everything on the same side, we have the post-collision state. So this is post-collision. Post-collision state of at the location x minus staggered delta t, velocity delta t half and half a time step before. So what does this mean? This means that what used to be the outcome, of a collision previously. So this is the outcome of the collision. One half time step before and 1/2 grid spacing away backward. Its velocity will become the pre-collision in the later time step. And this is also indicated by something that I cannot draw in 3 dimensions, so I have to actually go to 1 dimension. This is the characteristic diagram where I just draw 1 spatial dimension in this direction and 1 temporal direction in this direction. So I'm a little bit coming from the way of thinking about cellular automata, yeah, where we draw time downward. So I think you'll find other ways which are time upwards, but I used to draw time downwards. So here we have the lattice nodes, say, 1-dimensional, and then there is, then particles move from lattice node to lattice node in time, so along their characteristics. So this is a characteristic direction, because this is, they would have here 3 different velocities. This distance here we call delta x. This is the grid spacing, and this distance here is delta t, which is the time step. And then this is going on to the next time step. And so here in 1 dimension we will have 3 different discrete velocities. And the collision, which I write as c, would happen at these nodes, and the streaming would be in between. So there would be, there's a collision going on, particles collide, and after they collide, they stream to a new location, and then they collide again. So they will have a collision, a streaming, and yet a collision. And if you have such a splitting like this, you usually have a splitting error, because the question arises whether you do the streaming first and then the collision, or the collision first and then the streaming. Yeah? So if you split this up, you will have, you obviously have an error. So in order to avoid this error, and this may now maybe a little bit strange, because nobody tried to do this. It was only later, it's the observation, why is lattice Boltzmann actually not so terrible as it should be if you look at this? After doing this for 25, 30 years, somebody discovered, Paul Della discovered that lattice Boltzmann actually does something right. Yeah, and he could explain why this works much better than it's supposed to. Yeah. Okay. Let's so this I call this, maybe if somebody's writing down, this is streaming, and this is collision. So the problem is with all time integration methods that are not symmetric, which most time integration methods are not, because you know the past and you don't know the future, and therefore they are usually not symmetric. Yeah, so you have to invest extra work to actually get them at least second order accurate. Which, for example, with spatial derivatives is much easier. The only thing you need to do is to make it symmetric. Then it has only even order errors, right? So then it's always, it's either inconsistent or it's at least second order accurate. So how do we make this lattice Boltzmann second order accurate in time? This actually automatically happens if you just consider that you can split up this streaming into 1/2 is streaming, 1/2 is streaming, then 1 collision, then 1/2 is streaming again, and 1/2 is streaming again, and then the collision again. So you could write this thing like this. So you have a collision here, then you have 1/2 is streaming. So what is 1/2 is streaming? Actually, Paul Della first said, so I cannot split up the streaming, so I tried to split up the collision, which also works. So his idea was there's a streaming, then there's 1/2 a collision, and then another 1/2 collision, and then another streaming. And okay, I said, why don't you split up the streaming? He asked, well, how should I split up the streaming? What is a 1/2 a streaming? And I said, 1/2 a streaming is streaming half the distance. And oh, yeah. So, okay, you're streaming half the distance. So you do a collision, you stream half the distance, and you do stream half the distance again, and then you have a collision, and then you stream half a distance, and then you stream half a distance. Okay, so there is a problem with the ends, yeah? But the interesting thing is that you see is that this is a symmetric time step. This is a symmetric time step. So it's naturally either inconsistent or second order accurate, right? So, I mean, if you look at the old papers, they will say, so, okay, lattice Boltzmann is nothing else than just Euler forward integration, yeah? So, but it's pretty good for Euler forward integration, and this is, probably difficult to explain. But here it's very obvious because we have a symmetric time integrator, so it has to be at least second order accurate. It's only second order accurate. Okay, so this is important. By the way, this is called strung splitting, yeah? I've seen somebody writing strong splitting, or you could also say strange splitting. I don't know, but this is a guy who invented this, not for lattice Boltzmann. Okay. Now we need to get to some to see what this actually solves. So we have to do a Taylor expansion. Excuse me? Will you share these notes? Yeah. You can have to. I mean, we are hoping that we share the recordings, but you can also have this what I write down. Yes, of course. Okay. Because these things look a little bit ugly here, I will now say that this is Fij k plus, yeah, because it goes in positive direction, and I will call this here Fij k star minus, yeah, just to make it a little bit more compact, because we now have to go through these things. So because down here I will just Taylor expand this Fij k minus plus minus Fij k star, which is after collision is equal to 0. So this is what I want to Taylor expand. And you see, if I Taylor expand this, I have to Taylor expand this in space and in time. So I'll get a time derivative and I get a space derivative. And the step that I'm going is delta, for space, is delta t half Cijk, yeah? And for space is delta t half, right? So I will call this equation 1.1 because this is going to be important. So the first thing is, of course, I'm developing this, of course, at x and t, right? Obviously. So and in x and t, I'll get this ijk minus Fij k star. So I'll call this thing here Fijk. Because I don't want to write anything here now, it's Fijk at the position x and at time t, obviously. Yeah. So and then comes the Taylor expansion in time. So we'll have a time derivative that I write like this, and I have Fij k. So this is now because I'm going forward in time, yeah, with the pre-collision state, and backward in time with the post-collision state, yeah. Once I get plus delta t, and once I get minus delta t. So because I get minus delta t, I obviously get plus Fij k after collision. And with regards to the spatial derivatives, so I again have delta t half. So now these derivatives go in the different directions. So I have x, y, and z. So actually I have I can rewrite this. So for the students, I spend more time on this, but because you're so advanced, I have such an advanced audience, I immediately write down this is the velocity direction times, so this is a, what is it called? A directional derivative, yeah? So the direction in which we go times a scalar product with nabla on Fij k. Here again, we go, the pre-collision is in positive direction minus the post-collision in the negative direction. So we'll get here a plus again, Fij k after collision. And this is now truncated because this is both are symmetric. Yeah, the next term will disappear, and we'll have therefore something of order. Okay, now I can write is equal to order of delta t cube, right? So I put the order on the other side to save some space. Okay. Now, we did not talk about how we come from the pre-collision state to the post-collision state. Here we actually have a collision operator, and the collision, what is the collision? Okay, now it should not say operator because technically it's not an operator. Yeah, so it's the the effect of the collision is obviously what we have after collision minus what we had before collision, right? So in this Taylor expansion, it's the other. It's here the other way around. So we'll have a minus here, yeah, minus omega ijk. So this is what I call not accurately collision operator, but it's the effect of the collision because it's not it's not something that you apply to F, but it's something that you add to F. Yeah, so it's not actually. Okay, mathematicians should give me the right name, so I just call this collision, not operator. There are too many professors in this room now. For the students, it's a collision operator. Okay, so how does this collision operator look like? I mean, this is of course always the this is how lattice-Boltzmann methods are usually different. Yeah. So there are basically two ways where they are different. First is how do you discretize your velocity space? Yeah. So what are actually your speeds? So what is the range of ij and k? We'll come to this also. But the other question is how do we apply this collision? And this is actually where most of the knowledge now is. So it's a little bit complicated, so I try to simplify it somewhat in an maybe a little bit unconventional way. So what we usually do, what we almost always do, is we have a relaxation type collision, meaning we assume that there is something like an equilibrium. An equilibrium is the high entropy state, so the state with the most realizations, with the most micro-realizations. And the state where we start from is somehow driven towards this state. Yeah? So this can be done in a single, if we use a single relaxation time, where I said we have this state, we have that state, and we interpolate between these states, we can actually use the equilibrium and one relaxation parameter in order to write everything down. If we think, well, that's too simple, and we should actually have different time scales for different quantities, and then this becomes a little bit more complicated, but there is one paper by Pietro Asinari describing that you can actually describe these more complicated collision operators by what he called a generalized equilibrium. So the generalized equilibrium is unlike the real equilibrium, it is not only a function of the conserved quantities, but it can also involve some non-conserved quantities. Yeah, and I prefer, yeah, I mean this is a way that you can write it down. So I would now call this the attractor rather than the generalized equilibrium. This is the value where this one population of this distribution function. So each discrete point, yeah, here in this population, in this distribution function, we call population, yeah, because this is this is how many particles, or how what is the probability of that particular state to be populated. This is why we call it population. So we can basically say so that this thing here can be written as an Sijk, which is one relaxation parameter for that particular direction into Fijk attractor. So this is where it's driven to, yeah. So you could think about this like an equilibrium, yeah. But if we use different, more complicated than a single relaxation time operator, then this equilibrium becomes something. This attractor is something else than the equilibrium, right? So it can actually be really rewritten like this. So you can always rewrite all collision operators like this because you make it completely general, right? Minus F, the incoming population. Okay. So if you already know single relaxation time BGK operators, then you would say, okay, so this is the relaxation rate omega, and this would just be the equilibrium. Yeah? So if all relaxation rates are the same, then we can write it like this. If not, then that's a little bit more abstract. Okay, so now in this equation that we see up there, you see we always get the derivative, the different derivatives of the population before collision and the population after collision, right? And one question that drove the Lattice-Boltzmann community for a very long time is now which is actually the population at this time step? Is it the one before or the one after? Yeah. So the way we see this is that obviously, so the equations are for the average between them. Yeah, you add them up and to divide by 2. So I'll define this Fijk over bar is equal to 1/2 the one before collision plus the after collision. So, and I have consistency on this or the VirtualFluids group has consistency on this in our publications. Unfortunately, there are other groups that use the overbar for the pre-collision state and the non-overbar for the average. I'm sorry for this. You know, there's always a parallel world, and it's difficult to communicate with them if they're just being completely opposite to you. Yeah, this is like Mathematica and Maple. They made all the commands just the opposite, so that when you learn the one, you cannot use the other. Yeah. Okay. Sorry for this. So this is the one that we use. And now, if you think about this, it actually means that Fijk can also be written as Fijk. So because this is adding the collision to it, so it's actually, we can subtract half of the collision from the one in the middle in order to get the one before. Yeah? So we do this because we want to write the entire equation in terms of this overbar version, and in the collision operator, we unfortunately have the pre-collision state, yeah? So which we want to get rid of, yeah? Because this here is pre-call. This is pre-collision. So we can rewrite this omega ijk as Sijk into this Fijk attractor. Now we're replacing this with Fijk over bar. Now plus, because there are two minus, omega ijk half. And now you see, and this is, we cannot overstate how important this is actually. Yeah. So now you see that for this Fijk over bar, this has become an implicit collision operator. And so whoever said that Lattice-Boltzmann solves all of our problems, Lattice-Boltzmann would not solve any problems if this was not the case. Because if you think about this, this is a kinetic method. So we are talking about collisions of particles. So if you want to solve, the hydrodynamic equations by means of kinetic theory where you resolve collision of particles, you would have that extremely small time steps, right? Unless your collision operator is implicit, such that there is no time constraint on it. Yeah? And you see, for F over bar, this collision operator is implicit. And therefore, there is no kinetic time constraints. If this was not the case, nobody on Earth would use Lattice-Boltzmann. Yeah? That's extremely important. So, okay, what's...
Can we ask a question?
Yes.
Will you also explain how actually to derive this F equation, or is this assumed to be a prerequisite to this lecture?
The F equation. Okay, this is something I guess we forgot, but we'll point this out. So there are lectures online. Yeah, you can listen to me for 20 plus hours, explaining the prerequisites to this. Yeah, so I have a few lectures also on some kinetic theory where we start from the Boltzmann equation. I think this is what you mean, right? So if you look at this equation and you notice that this is minus the collision operator, then you already see that this is a discretization of the Boltzmann equation. And from the Boltzmann equation, you can derive the Navier-Stokes equation. And this is a little bit too much for today. Yeah. So we'll advertise the links to the videos where I explain all of this, but then you have to sit down for your hours, please.
Yeah, I didn't quite get why you're using this attractor in place of equilibrium function.
I can, because I'll when I go on, I will explain that we'll have different relaxation rates for different quantities that we observe. Unfortunately, it's not that simple that I can just take different relaxation rates in different directions. This is too simple. Yeah. But what I can do is I can make this the equilibrium. So if the equilibrium depends on some non-equilibrium quantities, then it works. Then you can actually translate this. So however, I'm not, somebody jumps on my back when I tell you that the equilibrium depends on some non-equilibrium part. The equilibrium can only always depend on conserved quantities, right? Therefore, so Pietro Asinari called this a generalized equilibrium. I call it an attractor. Yeah. So this is where this is going to. Yeah. But it's not necessarily the equilibrium. So actually, if there's only one relaxation rate, then it's the equilibrium. So, okay, I said that nobody would use Lattice-Boltzmann if this was not an implicit collision operator. On the other hand, everybody who uses Lattice-Boltzmann tells you that they use Lattice-Boltzmann because it's explicit, right? So how do we have explicit and implicit together? Well, it's very simple because you can put this on the other side, right? So you can just rewrite this, and just as you put this on the other side, and then you put it back, and then you get to Sijk divided by 1 minus Sijk by 2. Sorry. Fijk attractor minus Fijk, so the average, and this is, we like to write it like this: Fijk minus 1/2 by the power of 1/2 Fijk attractor minus Fijk. And some people who overbar, so some people who know Lattice-Boltzmann may have seen this if you replace this here by a single relaxation rate. So if now you come to this equation 1.1, you can rewrite this in the following way, that it's dt Fijk over bar plus this velocity Fijk scalar product on nabla Fijk over bar is equal, I put this to the other side, 1 over Sijk minus 1/2. And what I did here is I divided by delta t, so I have to divide by delta t to Fijk attractor minus Fijk over bar. And because I divided by delta t, is what we are left with is delta t squared. So it's the second order. So this thing here is a discrete Boltzmann equation, yeah. And from the discrete Boltzmann equation to second order, when you solve it to second order, you can derive the Navier-Stokes equation, which if you do it by hand will take you 30 minutes to an hour, depending how accurate you are. Yes. So this is the equation that we want to solve, and in the Boltzmann equation we can actually associate this relaxation time, yeah, as 1 divided by Sijk minus 1/2 delta t. So, and for those who know a little bit about Lattice-Boltzmann and have seen the single relaxation time method already, let's do just a simplification. So just assume that this here, that they are all the same, and the, bless you, the attractor is actually the equilibrium. So you can simplify it like this. Then you can identify the viscosity in the equivalent Navier-Stokes equation that pops out of this. Because I always have to, sorry for, I was, when I started, when I became a professor, I was horrified because I'm dyslexic, yeah, and I used PowerPoint for a long time, but I think PowerPoint is terrible for learning. So I decided that I just don't care that I'm always making mistakes, and the audience has to live with this. Yeah. So if I misspell something, just write it. Then okay, I'm trying I'm doing my best. So there is, sorry.
Can I ask you a question?
Yes, please.
I mean, you don't have to derive anything, but to get from this Boltzmann equation to the Navier-Stokes equation,
Yeah.
I guess you have to assume something on the F attractor or the equilibrium.
You have to assume something on the equilibrium, yes, but you also have to assume some, some order at which you cut off, in particular. Yeah.
But it's
Yeah, you
derive anything, it's just,
you have to the equilibrium. You have to assume pretty little, actually. Yeah, I mean, it needs to be Galilean invariant to a certain order. It has to conserve energy not energy. It does not conserve energy because Navier-Stokes equation, as such, does not conserve energy. Yeah, it has to. It has. So there needs to be an equation of state. There needs to be sufficiently Galilean invariance. And there needs to be a conservation of momentum and conservation of mass. And more or less, that's almost it, yeah? And some symmetry, yeah? Okay, so viscosity, the kinematic viscosity, that from kinetic theory, you know that this is this relaxation time, which is actually the mean time between collisions of particles, times the terminal velocity, which we a little bit simplify by the speed of sound, the square. Yeah, so this is the diffusion coefficient of momentum, and so Cs is the speed of sound. Cs is the speed of sound, and now the thing that are of most interest for those people who want to simulate very large-scale things, like if you want to simulate wind farms, then you want to have a non-zero. You don't want to solve the Euler equation, but you want your viscosity to be extremely small. Yeah. Therefore, what you're looking into is a zero viscosity limit. The zero viscosity limit, which is actually that tau is going to zero, and if tau is going to zero, this relaxation rate Sijk is going to 2. Yeah? And it's not, as in kinetic theory, it's not going to infinity. So you can actually do it, rather, because otherwise you would have to multiply by infinity. Yeah? If this was not the case. So, okay, let's write this. I always have this, these are my tutors. Yeah, Nabla is my tutor here. So this is stable for tau. So this is very important, that even that tau, the mean free time between collision is much, much smaller than the time step. This works. There is no kinetic. Let me just write this down. There's no kinetic time step constraint. Okay, I'm going to use more than 1.5 hours. So who is the question here?
Just could we maybe close the window?
Closing the window, so that one.
I can do it.
Okay, because people are, okay, I see people are getting, yeah, so please.
Speed of sound, can it also be a function of IJ, or is it like?
No, the speed of sound, of course, cannot be a function of ijk. I mean, it's not, the speed of sound should not be a function of the direction. The speed of sound should be isotropic. Yeah, the speed of sound obviously is a function of the temperature, right?
Yeah, but space.
So, okay, the speed of sound in lattice Boltzmann is a little bit a complicated topic that I can talk for 3 hours, if you like. The speed of sound in lattice Boltzmann so there is an optimal speed of sound for lattice-Boltzmann that leads to a lot of simplifications, which we usually use. The thing is, we only try to solve the Navier-Stokes equation, and the Navier-Stokes equation in itself does not care about energy. Yeah? The Navier-Stokes equation, I mean, you can amend the Navier-Stokes equation to conserve energy, but the Navier-Stokes equations themselves do not conserve energy. And therefore, it is sufficient to truncate the Boltzmann equation at a point before energy conservation is considered, right? So this means that unless you add something to it, yeah, energy conservation is not in this model, and therefore we choose a specific temperature, like you have a fixed temperature everywhere, and this fixed temperature leads to a fixed speed of sound. If you don't like this, you can, of course, I mean, then you need to model somehow the temperature field, yeah, can do with different ways, and which also has been done in VirtualFluids in different ways, yeah. So depending on whether you want to have a simple model, just a Boussinesq approximation, or you would actually like to have thermal expansion, right? So then you choose different models because one is more complicated than the other. And then, so if you have Boussinesq approximation, then you would not change the speed of sound. If you would have to have thermal expansion, then you would change the speed of sound. And in that case, you would have to change other things in the model in order to keep the isotropy. Because what is usually done with in the lattice-Boltzmann method is that you can reduce the numbers of degrees of freedom that you have by choosing a specific speed of sound, right? So if you have a truncated system, yeah, with only a few degrees of freedom, yeah, which would be anisotropic for any speed of sound, it can still be isotropic for a specific speed of sound. Yeah? And therefore, you choose that specific speed of sound in order to keep it isotropic. So if you want to have both things at the same time, this can also be done, but then we have to talk again. Yeah. So then because if you have a small velocity set, say from particle velocities, and you still want to change the speed of sound, then you introduce an anisotropy, and this introduced anisotropy can be compensated by choosing a different kind of anisotropy in the relaxation rates, which you choose in the opposite way, such that these two anisotropies completely compensate each other. I think we're probably getting a little bit off the topic by that question, yeah. But I mean, so this is something that I need another day explaining how this is done. But all of this has been done, yeah. You look more confused than before. Yes, here I assume a constant speed of sound. Yes. Okay, sorry for drifting so much off. Do we keep this in the recording? I don't know. Maybe it should. Okay, let's finally come to this velocity discretization. Velocity discretization, and we start here with 1D, and we assume that there is a particle or population that of particles having no velocity, that we call F0, and then we have one that is going left, that's going right, is F1, and one that is going left, that is F minus 1. And we are, and now this, so we write this minus 1 on top here of this. Let me see whether I can actually, and then we expand this. We do tensor product lattice. So VirtualFluids does not support 2D simulation. So there's only 3D simulation. Yeah. So there is we have, okay, we call this thing here 1D, and we have 3 speeds, D1, Q3, and now we go from to D3, Q, 3 by the 3, so this would be D3, Q27. And the thing looks like this. Okay, because I'm at the end of the page, I have to make this a bit smaller, I guess. I hope you can just so make out the different directions that is written here in this so-called Miller indices. Maybe I'll put this bit here. So this is indexed with so-called Miller indices. So if you ever studied something with regard to crystals, then you will know what Miller indices are. So this is the direction of crystals, or the directions in lattices as for crystal direction. So this ijk, they are all elements in what we call -1. So this is the way this is written in Miller indices, -1, 0, and 1. So, okay, spent too much time, but you also had questions, so this is my excuse. So now we have to design a collision operator here, and I already indicated we are not using the very simple single relaxation time collision operator, but we want to separate out different quantities. And the quantities, so that the first idea of what you could, if you think about these probability distribution of finding a particle in a velocity and in a position, that what you would usually do is you ask about the moments of these things. Yeah, they have a statistical function, and you want to get these moments. And moments can be defined in a different way, and the most basic one is what we call the raw moments, and of these raw countable moments. Raw countable moments. So everything that's called a moment is you integrate a distribution over, you multiply a distribution by a function, and then you integrate this. This is what is a moment. Yeah, and in particular, these raw countable moments, they can be defined from a moment generating function that now looks like this. This is going to be a little bit ugly. So countable moments means that we propose that there are infinitely many moments, yeah, that the information that is in these distribution can be transferred to infinitely many moments. Yeah, and because we are in 3 dimensions, these moments have 3 indices. Yeah, because we integrate over the x velocity, the y velocity, and the z velocity. important, we are not integrating over space and time, we are integrating over velocity. Yeah? And these moments can be obtained from a moment generating function. And in this, now I have to write all these ugly letters, which I probably write completely wrong. Let me write it down and then I explain. So we'll have like a frequency, xi, yeah, and we do the 8, so this is the first index, the 8 derivative in this first index, in this first xi, variable xi, and then I'll try to write a capital upsilon, which I cannot write. So we do a beat derivative in upsilon, and we do a seed derivative in zeta, capital zeta, and this we apply onto the Laplace transform on the distribution function, and we evaluate this at the frequency 0. So what we mean by this is we have a microscopic velocity space xi that is composed of the components xi, which is the x direction, small upsilon, which I cannot write, in the y direction, and small zeta in the z direction. And of these, we define a frequency space, which we write by the capital letters. So we'll have this capital xi is composed of xi, upsilon, which I cannot write, and zeta. So, and this f is obtained by a bidirectional Laplace transform. You can also take it from a Fourier transform. This is doing the same thing. So this f of capital Xi it's bidirectional, so it's going from minus infinity to infinity over f as a function of their velocity. Now we have discrete velocity, but this is also true for non-discrete velocity, into e by the power of xi times, so this is a complex frequencies, e by the power of capital Xi times small xi, and integrated over all the three directions. And now I have too many professors in this room. This is actually the inverse Laplace transform because it has the different sign. I don't know how this came about in the original derivation, but it has the opposite sign than what is usually used in the Laplace transform. I'm sorry. Yeah. So usually we have a minus here, and in the inverse we have a plus here. So it's actually the other way around, but don't bother. Okay, so because now we have a discrete, this f is discrete, we can actually rewrite this as e by this here. Oops, not very ugly. No, we have a discrete distribution, so the discrete distribution actually comes with Dirac delta, yeah, functions, and I'm annoyingly, I will now annoyingly become very unphysical here by just saying that the velocity space has velocity 1 minus 1, yeah, because I don't want to, so this xi, yeah, and I is the direction, yeah, but say it has the velocity 1 in that direction because I don't want to bother with all the units because the equation is long enough. Yeah. So you see, this I is actually a velocity. Therefore, I can subtract xi when it's in the same units as in the letters. Yeah. So there are these three delta functions. And k minus, what is it, zeta. So, and this integrated over everything here, and IJK, Fijk is missing. Yes, thank you. I mean, it's okay, overbar or not overbar, yeah. So the good thing is, I mean, the Dirac delta function, you integrate over Dirac delta function, so it's taking out the particular points in the integral, and so this actually simplifies such that we can write such that if we take these derivatives later for MABC, the integral can be simplified to ijk, in this case going from -1 to 1 over Fijk, and it's I by the power of, how ugly can I write? I by the power of A, J by the power of B, and K by the power of C. So you'll often see in the literature saying that moments are defined like this. I mean, I would rather say this is the simplification of what drops out, because this is important for what we need to do later. Yeah, you can simplify the moments to this, but they are defined by this Laplace transform and the discretization. So now, if you want to derive the Navier-Stokes equation or other equations that this equation here may actually solve, by the way, I mean, you can write overbar. You can, yeah. So this, so the one without overbar gives you the moments of the pre-collision. The one with overbar gives you the intermediates. Now, the equations, the equivalent partial differential equations that you actually solve by this method, hydrodynamic equations, they actually come from this moment hierarchy. Okay, I cannot write this word. So what? Because if you take the moments of this equation number 1, where we had of the Boltzmann equation, yeah, and this is also true for the not only for the discretized Boltzmann equation that we use here, but for the Boltzmann equation in general. If you take moments of the Boltzmann equation and you truncate, then you get to the Navier-Stokes equation, yeah. And the reason why the way this happens, if you take these moments, what you end up with is, for example, you take the moment the moment A, B, C of the entire equation, then you get the time derivative of that moment plus the spatial derivatives of now A plus, so in X, A plus 1, B, so the moments, this is why it's important that they are countable. They are counted up. They are counted up together with their derivative with which they appear. Yeah. So you see, if this here is mass, right, then you get the derivative of velocity. So change in mass depends on the derivative of the divergence of velocity, right? So you already see where this is going to, right? Plus dy m, so A, so now it's B is counted upwards, and actually the word sets MAB C is counted upwards, and apparently I've forgotten here something in my notes. So what you also get is you get a collision. I guess we get it with a minus. We also get a collision of A, B, C, and this is equal to, yes, then in this case it will be equal to something delta t square. now you can identify these moments with rho. Yeah, so it always we are not very accurate with our units here. Yeah, because this is the mass inside the small volume that you could associate with one lattice node. So is this now mass or is it density? It depends on whether you divide it by. Yeah, so we're a little bit inaccurate here. You call this rho and say this is mass. Yeah, and then the first moments like this would be the momentum. So we have u times rho. We would have for the y direction, we have v times rho, and for the z direction, we would have w times rho. Actually, this is not the nomenclature that is in use for virtual fluids. We call it. I'm not completely sure whether we do it always consistently, but it's v1, v2, and v3, or vx, vy. Yeah, it's probably not. We are probably not consistent there ourselves. So these things here are the momentum. And then you can also actually get the pressure. So pressure in lattice Boltzmann is something that you can go on talking forever. So if we subtract, there are different definitions of pressure. So this would be 3 times the pressure. So this is the trace of the second order moments minus the kinetic energy of the fluid. Yeah, and this is 3 times the pressure that comes out in the Navier-Stokes equation. Okay, so important for going onward is that the viscosity, which is the one parameter that we have in the Navier-Stokes equation that we physically have to adjust to get the right Reynolds number, yeah, this is related only to the relaxation rates of the second order moments. So the order of a moment is the sum of its indices. This is the order, yeah, and the viscosity is related to the relaxation rates only of the second order moment. So this is important because the other moments, they have a free relaxation rate, or they have a relaxation rate that's not constrained by hydrodynamics. Yeah, so these moments that we have to adjust according to hydrodynamics are the moments M110, M101, and M001. And in addition to these, so there are actually 5 of them, this is M200 minus M02, M20 minus M002. Yeah, and this trace here, is not actually related to the shear viscosity, but it's related to the bulk viscosity of the fluid. So if you have an incompressible fluid, which to leading order you have here, this does not appear in the Navier-Stokes equation. Okay, so now all of this is in preparation of what we want to do in virtual fluids. Yeah, so because we want to. But there's my other tutor, is the one who's asking the questions. Because we want to know how to deal with the other moments. Now I'm halfway through my lecture almost, and I'm through all of my time. But I heard I have 20 minutes more. So let's see whether we get to all was introduction. So how do we deal with all the rests? Of course, we deal with this by using multiple relaxation rates. Yeah, and actually, what we mean by multiple relaxation rates, unfortunately, or relaxation times, unfortunately, there is a method that is called like this. So usually, this is something extremely specific. Yeah. Which we are not doing it that way, we are doing it a different way, but we are also using a multiple relaxation times. So this is now not the MRT method, as it's called. Because what the MRT method was actually missing out is to properly separate these variables. Now it's extremely important if we propose that we identify different quantities that evolve on different timescales, that these quantities are independent of each other. And this is something that, everybody is nodding on this. And the problem is, how do we define independence of each other? So it's not just they are if you have children and they grow, yeah, their height is obviously not independent to their weight. Yeah, even though you can be small and thin and small and fat, and yeah, that makes, in that sense, it is kind of independent, but it's correlated, right? So, and now you would assume if your child grows at a certain speed, then its mass also has to increase in some proportion to that speed. So these two things are not independent of each other. Now you have to identify. So this is why there's why these maybe body mass index or something, right? So you have to identify quantities that are really independent of each other. Yeah, and the Lattice-Boltzmann community has struggled for kind of 20 years to identify the right variables to get these things apart, so that you can actually say, so this evolves on a different time scale than the other one, yeah, because they are not correlated. And in the MRT method, this is not done correctly. And now, whether we do it correctly, yeah, but I think we do it less incorrectly than the MRT method. So, okay, our challenge is we have to identify independent statistical quantities of the distribution because I write this down because this is so important. Only independent quantities can evolve on different time scales. So, and for this, we return to this moment generating function. So, which is f as a function of xi is this integral f xi xc times big C integrated, and this gives, okay, so this is, F is a function of all its moments, right? So, and this F is kind of a probability, probability distribution now in, you could say, in frequency space. So we just changed the space. So the speed variable goes to a frequency variable. Velocity frequency. Unfortunately, it's not very intuitive what this means. So what do we know from statistics about independent variables? Independent random variables. We know that this leads to a factorization of the joint probability. So if two things are statistically independent of each other, so two events are statistically independent of each other, that they occur at the same time is the product of each of them occurring individually, right? So, and this is this thing that we are going to use to define what we mean by independence. So factorization of the joint. So right. So the good thing is the factorization is also true not only for the probabilities but also for the probability density, so for the distribution. Okay, so this means if we have this distribution f that is a function of moment 1 to moment m, moment n, say, then we hope that we can rewrite it in terms of a product of individual distribution functions of which each only depends on one variable, right? So this is what we want to have. So in this CE, this should be then mutually statistically independent of each other. So I was told that I start 15 minutes later, so then I can talk at least 15 minutes more. The problem is the following speaker is me, right? So moments don't do the job. Moments, MABC, as we have seen, are these, we take the derivatives of the moment generating function, which is this Laplace transform, F. And we evaluate this at the frequency 0. So what is this? You take a function, you take increasing derivatives, and you evaluate them at a specific point. These are obviously the coefficients of a series expansion. This is exactly what you do in a Taylor series, right? Just that the Taylor series includes this 1 over the thing factorial. Yeah, that's the only difference that you have here. So these are the coefficients of a series expansion. Which means you can rewrite the entire thing in the opposite way. So you can recover the moment generating function as a sum from A, B, and C from 0 to infinity is xi by the power of A, epsilon by the power of B, and z by the power of C divided by, what I just said, A factorial, B factorial, C factorial, and here comes the moments, M, A, B, C. Yeah, this is just the Taylor expansion. So these are the coefficients of the Taylor expansion, and then you put them in the Taylor expansion, and then you get back the function. Always assuming that you can expand these things in a Taylor series, of course. Yeah. Which you can do, by the way. Okay, I'm using up my time that I don't have, but you can do this because it's in frequency space. Yeah, because the distribution itself was discrete, and in the real world, particles are also discrete. Yeah, so then you cannot easily Taylor expand them because they are single particles. But if you have a discrete distribution, you take the Fourier transform, you get a Fourier Laplace transform, you get a continuous function, and of this continuous function, you can take a series expansion. Yeah, so this is one reason why we go to frequency space. Okay, now I lost where I'm here, yes. So now these are not independent variables. What do we have to do if we want to see independent variables? So say for independent variables, so we have this f of xi. We said that if we can factor this in its independent parts, which we have not yet identified, fi and ci. So if we want to write this not in this product, but in form of a sum, because we'll see that we have a sum here, then what we have to do, obviously, is we have to take the logarithm of the product. So we'll take the logarithm of f of xi, and this becomes the sum of I from 0 to infinity, the logarithm of these now independent guys, fi and ci. So therefore, now we have it as a sum. Yeah. So if we take, now, basically what we have identified is when we take these moments, not of the f itself, of the Fourier of the Laplace transform itself, but of the logarithm of this, then they are automatically coming out as independent variables. And therefore, we now define the cumulant generating function Okay, so these C's we call cumulants. Yeah, we take the logarithm of this f of xi, and this is the sum of a, b, and c from 0 to infinity, over xi, a, epsilon, b, zeta, c. Okay, you're always trying to say if I'm doing something wrong, right? So big C, A, B, C, and this now can be rewritten as we get A, C, A, B, small c is now these derivatives. So we invert this function again as we had them before. B, zeta c, the logarithm of the Laplace transform of this function, and we evaluate this xi again at frequency 0. And now what we are going to do is we applying MRT with cumulants. So this is one part of the theory of the cumulant method where we get actually to this idea. Now having the idea, so I have to admit the idea between the idea of doing this with cumulants to the published paper took 8 years, because computing cumulants is not that straightforward for several reasons. One is, I mean, if you see this equation, do you immediately know what you have to do? Okay, even though we are running over time, I'm telling you what we do. Yeah. Okay. In the afternoon, I'm telling you really what we do, but now just. So computing cumulants. How does this work? Say we want to compute C001. Yeah. So then we'll take the first derivative of zeta in the logarithm of f, and we evaluate this at xi equal to 0. So doing this directly is difficult, but what we can do is we can apply the chain rule of differentiation to this. I mean, we have the logarithm, yeah, and if we apply the chain rule on the logarithm, what we get is 1 over f, and this into d set f and xi equal to 0. Now this d set f is obviously the definition of a moment, right? So what we can now do is we can, in this applying the chain rule, what we can do is we can write the cumulants in terms of their moments. And then we can compute the moments and then turn them to cumulants, then we relax the cumulants, and then we do the entire thing backward, yeah, which is complicated in itself. So what you observe is f is no derivative, yeah, no derivative. If you take no derivative for xi equal to 0, then you get the 0-order moment. So what we have down here is m000, and what we have there is the first moment, so it's m001. And this is the velocity in the z direction. Yeah? So when we take C002, then we get the z second derivative logarithm of f. So the easiest way you can do this is you just take this guy here and take a derivative of this again and applying the chain rule. So we get here d set f squared divided by f squared plus d set the second derivative of f divided by f, and we'll evaluate this at xi equal to 0. Now what we have here is obviously minus and twice the m, you have m001 square divided by m000 square, so this is w square, plus what you have down here is m002 divided by m000. Yeah? So now if you put, you remember that the pressure was somehow related to the trace of the second order moments minus the energy. Now you see we have here, or pressure. Okay, it was not very accurate. It was actually the because it was an expansive extensive quantity. It would actually be the energy, right? And I mean, pressure times volume is energy. Yeah? Now, what comes out as the cumulants are all intensive quantities. Yeah, you see, velocity comes out, and the C002 plus C020 plus C002 is what we call the theta, we call the dimensionless temperature, because we would have to multiply this by a Gauss constant. This is actually the temperature. So I don't know, I mean, no time, again, well, going over time, but this is actually something pretty important. So how do you explain your children what is temperature? You see, this looks, from the outset, it looks terribly abstract, these cumulant things. But what drops out is the velocity and the temperature, right? So things that we have known for eternity, the things that you can touch, that you can observe, right? The things that you naturally observe, they are actually the cumulants, because they are the independent intensive quantities that you can observe in nature. They drop out of this theory. Very simple, please.
Is the C000 here would become then logarithm of density?
Yeah, so C00, you know, we don't talk a lot about the C000 because it's anyway a conserved quantity, so we don't need to care about this. Yeah? Yeah. Okay, so first cumulants is velocity. The trace of second cumulants, second order cumulants, is temperature. So, very terrible. So how much more theory do you can you swallow now? Yes. Okay. We'll have a break now, and then we'll actually continue with theory one later. I have to. We have to stitch the recordings together. Yes. Okay. We'll somehow manage this, right? Okay. What did I do?